So good afternoon, everyone. I'm Supriya Sharma from IIRS, and this session is on Google Earth Engine APIs, an introduction and case studies. So these are the topics that we'll be covering today. We'll first see what is the Google Earth Engine and how it works. We'll discuss why it is such a powerful platform. Then we'll discuss how you can get started with the Earth Engine, and we'll also cover a few applications and case studies that have been performed over the Earth Engine. So the Google Earth Engine is a cutting-edge technology that simplifies the analysis and visualization of geospatial datasets. So earlier what you would have to do is you would have to first search for the data that you want to work on. You would have to download that data. Then you would have to search for the platform or the application on which you want to analyze your data. You would have to download that application. You would then import your data onto the application, and then you could start with the actual processing or analysis of the data. But with the help of Google Earth Engine, you have access to a multi-petabyte catalog of analysis ready data, which is geometrically corrected, it is atmospherically corrected, and this data is radiometrically corrected. Now, this is a cloud-based platform using which you can detect changes over the Earth's surface, you can study trends, and you can quantify these changes. And you can do all of this without getting involved in complexities of cloud-based computing. So how it works is there are several storage and compute servers present at Google data centers. There are also certain algorithms associated with these data sets that are present on these servers. So how you perform any operation over these data sets is by writing code. So you can write code for the simplest of operations such as basic bank math calculations, or you can also perform calculations such as machine learning operations using these codes. So when you write a code and when you submit it to the Earth Engine, it gets converted into a set of instructions which is sent to the Google servers. Now these instructions are split across different machines and the computation is performed in parallel. This result is assembled as a single unit and it is sent back to the user. Now the user will only get what the user asked for. So if the user asked for a bar chart to be generated or a graph to be displayed or an image to be displayed, only that result is sent back to the user. So all the computation is performed on the servers and only a small part of the result which the user desired will be sent back. So this consumes a very low bandwidth. Okay, I can see some messages in the chat box that certain noises are appearing in the background. Please give me a minute to resolve this. So am I audible clearly now? So I'll just briefly explain this again. So the Google Earth Engine, this is a cutting-edge technology that simplifies the analysis and visualization of geospatial datasets. Now this is a cloud-based platform and it lets you detect changes over the Earth's surface, and lets you quantify those changes, detect some trends or patterns, and all of this is performed on the cloud, and you don't get involved in the cloud-based complexities. The complexities of how this calculation is parallelized across multiple servers. So you don't have to get involved with any of that. You have to use the API provided by the Google Earth Engine, and the servers will perform your calculation for you and will send you back the result. So this is like having a supercomputer at your own desktop. You can use the power of the different servers present over the Google data centers. You can access their power from by sitting at your own very own systems. So the Google Earth Engine has a wide catalog of analysis ready data. This is geometrically corrected, it's atmospherically corrected. This data is also radiometrically corrected. And using the Google Earth Engine, you can perform global scale analysis within a matter of minutes. So how this works, how the Google Earth Engine works, now you can perform analysis on the Google Earth Engine by writing code. So you can write code for the most basic operations such as bank math operations. You can also write code for computations such as machine learning as well. So when you write a code, this code gets converted into a set of instructions which are sent to the Google servers. At the servers, these instructions are executed parallelly across multiple machines, and the result is compiled and it is sent back to you as a single unit. So you get only what you asked for. So if you want a map to be displayed, or suppose a bar chart to be displayed, so only that part of the result will be sent back to you. So all the calculations required to generate that chart will be performed at the servers, and only the final output will be sent to the user. So this saves a lot of bandwidth. Now the Google Earth Engine is a powerful platform for a variety of reasons. The first of them being its wide public data catalog. So the Google Earth Engine hosts more than 40 years of satellite data, covering more than 400 data sets. It contains more than 20 petabytes of data, and more than 6,000 new images are added to the Google Earth Engine every day. Now the time period between the acquisition of an image and its ingestion into the Earth Engine is usually 1 to 2 days. This means that if an image is acquired today, it would be uploaded to the Earth Engine by tomorrow, or at the maximum by day after tomorrow. The Google Earth Engine contains imagery from the Landsat series. This includes both the top of atmosphere reflectance data as well as the surface reflectance data. It also includes images from the Sentinel series, which is at a 10-meter resolution. Data from the MODIS series is also available on the Earth Engine. Other than that, there are several datasets available which cover land use land cover datasets, terrain datasets, atmospheric datasets. There are a lot many datasets which you can also filter out by going through the public data catalog. You can browse through the data catalog and you can filter the datasets as per your requirement. And other than the data that is already available on the Earth Engine, you can upload your own vector and raster files on the Earth Engine, and you can work with your own data. Another reason why this is powerful is its high processing power. So the Google Earth Engine automatically parallelizes the computation across many servers. So the request that you send to the Earth Engine is split into different units, and these units are computed parallelly. Finally, the result is reassembled and it is sent back to the user. The Earth Engine also follows a lazy computation model, which means that at any point in time, only that much calculation will be performed that is necessary to fulfill the current request. So depending upon your browser's zoom level or the boundary of the browser, the Earth Engine will determine that how many pixels the result has to be calculated for. And only those pixels which are currently visible, the result can be calculated for only those pixels. When you further zoom out of this map, Then further, more number of pixels arise, and again new results will be generated for the new pixels. The Google Earth Engine also has several inbuilt scientific algorithms which are optimized for use over parallel processing platforms. And the Earth Engine also has a judicious caching mechanism, which means that all the expensive intermediate results are stored in the cache memory. So when a similar computation needs to be performed again, it need not be recomputed, but the result can be directly fetched from the cache memory and be used for further calculations. So all these features ensure that the result is computed or the calculations are performed at lower costs and at very high speeds. Another powerful feature is that you can save and share your work. So we already saw that we can import our data into the Earth Engine. Other than that, we can also export your results to your Google Drive and eventually to your desktops. So from there, you can import it into any third-party application with which you want to further analyze this data. The Google Earth Engine also maintains versions of your code. So by default, all the versions of your code will be maintained by the Earth Engine. And at any point in time, you can go to a previous version. You can compare your current code with the previous version, and you can revert back to a previous version if you require to do so. You can also share your code with other users. So if you're working in a team or if you're collaborating with others, you can share your code with them. And if you don't want to share the code, if you only want to share your analysis, then you can choose to create applications which are alike to both experts and non-experts because no code is shared here. This is just an interactive application using which the user can determine the different outputs that can be generated by your code. The Google Earth Engine has very powerful interactive development platforms. So we have the Google Earth Engine Explorer, which is mainly used by non-specialists only for viewing purposes. This has very limited analysis capabilities, but the application programming interfaces are far more powerful. The Google Earth Engine provides both the JavaScript API and the Python API. The JavaScript API has all the Google Earth Engine library functions along with the visualization functions. So using the JavaScript API, this is a browser-based API. Using this API, you can visualize your results on your web browser. The Python API, although does not have the visualization features of the Google Earth Engine, but the advantage with the Python API is that you can use not only the Google Earth Engine library functions, but also all the Python library functions that are available. Both of these APIs have built-in tools which enable you to perform complex analysis, and they enable global processing with just a few lines of code. None of these APIs require you to have extensive knowledge of GIS or any scripting language. So this is what the Google Earth Engine JavaScript code editor looks like. In the region labeled 1, this is the area where you write your code. On top of this, we have the import section, and this is where you can import any data sets into your code. On the top of this code window, we can see we have a get link function, which enables you to share your code with other users. So you can just get a link of your code and copy and paste that link to any user that you want to share your code. We of course have the save button to save your code. The run button is used to run your script. The reset button will reset everything that has been added to the map or to the console where the outputs are generated. So it will basically reset all the outputs. The apps button will help you generate or create applications from your code. The region label 2 is where your results are displayed in the form of layers added to the map. So on the center, you can see that a Landsat image has been added to the map. On its left, you can see There are certain geometry tools available. These tools can be used to draw geometry on the map. Below that, we have the zoom buttons to zoom in and out of the map. On its right, we have the layer manager, which lets me control the different layers that I add to the map. In the section labeled 3, we have 3 tabs, the first of which is the script manager. So this lists down all the scripts that you have created on the Earth imagery. So this is different for every user. All the scripts that the user has created will be displayed here. The docs tab is for documentation. So this contains a list of all the functions that are available with the Google Earth engine. The assets tab is used to help you to import your own data onto the Earth engine. On the very right, we can see the region that is labeled 4. We firstly have the inspector tab, which lets you assess the value of each point on the map. So if I click on the inspector tab and I go to my map and I click on any point on the map, it will give me a value of all the bands for all the layers that have been added to the map at this particular point. The console is where the print statements are printed. So if I give any print statement from within my code, the result will be printed on the console. The task manager is used for the export part. So the asset manager on the left was used when you import some data into the Earth engine, and when you want to export your results, you use the task tab. So let us discuss the most fundamental data types that are available with the Earth engine. So when we talk about raster data type, the most fundamental data type is an EE.image. Now anything that starts with EE on the Earth engine is a server-side object, and everything else is a client-side object. So an EE.image refers to a single image. For example, one Landsat image. So an image can be composed of several pixels and can have multiple bands associated with it. It can also have several metadata properties attached to it. An image collection refers to a set of images or a time series stack of images. So if I say the collection Landsat 8, it would mean this all set of Landsat 8 images starting from the very first date of image acquisition till the very recent Landsat 8 image. Then we have vector data types. So the most fundamental vector data type on the Earth engine is EE.geometry or EE.feature. So this can mean a point, line, or a polygon. A feature collection would again be a set of multiple features. Now these are certain functions or operations that you can perform over the Earth engine. The map function is a very useful function which lets you perform the same operation over all the objects in the collection. So it is basically like a for each loop which performs the same calculation for all the elements that are available. So let's say if I want to analyze or if I want to calculate NDVI of 50 Landsat images. The first option would be to take each image one by one, apply the NDVI formula, and go to the next image. But this would defy the very objective of programming. So we use the map function here. So using the map function with just a single line of code, we can perform the same operation over 50 Landsat images. And this number can be 50, it can be 100, it can be 1000. Then we have the filter operation, which lets you restrict your analysis in some way. So if I want to perform some calculation over Landsat collection, but if I want to limit my calculation only to India, the region of India. So I need all the images of the Landsat collection which are covering some part of India. So by this, I am limiting my collection with respect to region. if I don't do this, if I don't limit my collection in some way or the other, there are millions of Landsat images already exist. So for that purpose, we can filter our collection on some basis or another. Another means of filtering the collection will be on the basis of date. So let's say if I want Landsat 8 images starting from 1st January 2020 to 31st December 2020, then I would be limiting my collection with respect to time. Then we have the reducers. So reducers are used to generate some statistics from the data or aggregate the data. So statistics such as mean, median, max, min can be generated from our data sets. Machine learning operations can also be performed over the data that is available on the Google Earth Engine using several functions that exist as a part of the Google Earth Engine library. Bank math operations can also be performed. You can subtract two images. You can multiply an image with a constant value. You can mask out certain pixels in an image. Then we have the UI elements, which are used to make your application more interactive. So these elements are a button, checkbox, some drop downs. All these elements can be added to the application to make it more user-friendly. Now, these are the basic steps involved in the talk about how to perform any kind of analysis over the Earth. So the very first step would be to import your data. So firstly, you would import your collection. You can choose to filter the collection. After your data is ready, you would perform whatever analysis it is that you want to perform over the data. After that, you can choose to either display your result or export your result to your own systems. And optionally, you can choose to create apps and share this result or this work with other people. So when should you use the Google Earth Engine? The Google Earth Engine should ideally be used when you want data coverage for a large region. The advantage is that you don't have to download the individual images. The data set is already available with the Earth Engine. You just need to write a single line of code for filtering this data on the basis of the region. So it lets you perform calculation over very wide areas. And also when you want to study data covering a large span of time. So the Google Earth Engine is ideal for use for advanced raster processing, but we see that it is not really recommended for very heavy vector operations because the analysis capabilities of Google Earth Engine in the vector area are relatively less as compared to the rasters. Another thing that you cannot control over the Google Earth Engine is the parallelization. So you cannot control the details of parallelization. You cannot control how many machines your data is the analysis is being performed and how your data is distributed. So all that is not controllable by the user. So if you want to control the details of how parallel processing is performed, then Google Earth Engine might not be the right. So one example of the several data sets that are available on the Earth Engine is the Global Surface Water Occurrence Map. This is available on the Google Earth Engine and is used for monitoring the change in intensity of surface water across the globe. So this maps the loss and gain of water. It tells you the seasonality of water, how many seasons, how many months out of the 12 months in the year this water is usually present. This dataset has data from the year 1984 and can be explored on the Google Earth Engine. This was one of the longest calculations. Generating this dataset was one of the longest calculations that has been performed over the Google Earth Engine so far. So it is a very wide dataset. Now we know that the in situ methods are expensive. They are physically challenging and of course require a lot of time. We also know that remote sensing is cost effective. It can be performed across the globe. It can be performed at high frequency depending upon the data that we intend to use. The Specific advantage of Google Earth engine in geospatial analysis is its high processing speed, the fact that results can be generated on the fly. So when you run your code at that very time, the result will be computed on the service and it will be sent back to you. So result is computed as you go. There is also a possibility of automation. So you can create end-to-end automated applications using the Google Earth. Another advantage is that you write once and apply anywhere. So if you write a code for one region, the same code could be used over any other region on the entire Earth, provided that the data sets are same. Also, you can share your work, which we have already discussed, that your work can be shared with other people very convenient. So let us discuss a few applications that have been built at IIRS using the Google Earth engine. So firstly, we have the forest cover loss detection. So we know that biodiversity is fundamental, of course, to fulfillment of human needs, and it offers wide options for sustenance of human welfare. However, the recent trends of overpopulation, industrialization, and urbanization are causing forest loss. And forest cover loss is not only a matter of national, but it's a matter of global importance. So, with this in mind, we at IIRS have developed an application to detect the global forest cover loss in date. So, this application detects the areas where the forest cover has been lost, and it generates the statistics such as the area that has been lost. It compares the forest cover loss across various states and studies the variation in forest cover loss over the years. So how the forest cover is increasing or decreasing over 18 years. So this maps the forest from year 2000 to 2018. So for this application, the Hansen Global Forest Change dataset has been used. This is a freely available dataset, and it can be accessed using the Earth engine. Certain parameters that are available with this dataset are the tree cover that is in the year 2000. So this part is used as the base data. The tree cover in the year 2000 is used as the base data, and any loss and gain is computed over this. So we also have a band called loss of tree cover, which indicates whether the forest at a particular pixel has been lost or not. So this particular band will have a value of 1 if a forest pixel has been lost. It will have a value of 0 if the forest pixel has not been lost. We also have a field called year of loss, which indicates the year in which the forest was lost. So the year of loss field varies from 1 to 18. So the value of 1 means that this forest pixel was lost in the year 2001. The value of 18 means this pixel was lost in the year 2018. There is also a band called gain of tree cover, but this gain is only till the year 2000. We also have Landsat 7 bands, which indicate the satellite image for the base year, that is the year 2000. On your right, you can see that this is India and the Hansen forest cover dataset applied over this. So the green areas indicate the presence of forest. This is the base data from the year 2000. The red patches indicates the areas where the forest has been lost. So we can see ample forest cover loss in the northeastern part of the country. So this is the user interface of the map. So on the right hand side, we have the input panel where we let the user select the state. So the list of all Indian states is presented here. The user can select the drop down and pick the state. Then these statistics are generated the total surface area, the total forest area, the percentage of forest area, how much forest cover has been lost, and what percentage of forest cover has been lost. Also, changes in the forest cover in this area, in this state over the years is being represented as a bar chart. And the layer is also being added to the map. So the green layer indicates the forest cover and the red patches indicate areas where the forest cover has been lost. So when we zoom in, we see that these are the pixels where the forest cover has been lost in the state of Assam. And these red pixels indicates areas of forest loss. So if you see this red patch over here, the next slide will be zooming this area and we'll see how the forest has been lost over the years in this particular region. So this is that area that we saw in the previous slide. We can compare the images on the left and right. The left hand side image is from the year 2000. You can see dark green patches here which indicate the presence of forest. However, when we see the image from the year 2018, we see that no forest remains in the area. And this can also be observed from the Hansen dataset, where we see that the red pixel indicate the area where the forest has been lost. So approximately 107 square kilometers of forest was lost, and the maximum loss occurred in the year 2004. This can also be seen from the chart that is generated here. You can see a steady decline in the forest cover from the year 2001 to 2012, after which it has been more or less constant. This is the region next to the previous region. This is this region over here, this red patch that you can see. This is also a part of Assam, and you can see from the image, by comparing the left image and the right image, that the forest cover has been lost. This can be verified with the Hansen data set, and also this chart that has been generated indicated that till the year 2012 there was constant forest loss in this area, after which it is more or less steady. And this accounts to somewhere around 36 square kilometers of forest loss. Similarly, in Arunachal Pradesh, we can see, if we look at this patch, and if we zoom into this patch, you can see that there was ample forest cover present here in the year 2000, which has been completely lost in the year 2018. Again, it can be verified with the Hansen dataset. So if we compare the forest cover loss by different states, we see that states of Assam, Mizoram, Nagaland, Arunachal Pradesh have lost a lot of forest. And this is the forest cover in India from the year 2001 to 2018. You can see a steady decline. Also, in which year how much forest cover was lost can be calculated and mapped. Another application that we built here at IIRS is for water quality parameter analysis. So inland water bodies we know provide us various domestic and industrial uses, and they aid in sustaining the ecosystem. They are also responsible for carbon cycling. However, the quality of inland waters is decreasing with the increasing human population. Therefore, it becomes essential to monitor and assess this water quality. Turbidity is one important indicator of water quality, and this can be used to assess the extent of pollution in the water body. Chlorophyll could be considered an indicator of the productivity of the water. So for this, an application has been built at IIRS, which measures the water quality using Sentinel-2 images. So it maps three water quality parameters, which is the turbidity, Secchi depth, and chlorophyll of inland water bodies. It is an interactive application. It lets you filter data according to your own requirements. Atmospheric correction is performed over the filtered data, and after that, these parameters are mapped. The results are visualized and exported in the form of both images and graphs, also animations. So for this, top of atmosphere reflectors data from Sentinel-2 series is used. Sentinel-2 has a spatial resolution ranging from 10 meters to 60 meters for different bands. A swath width of 290 kilometers, and Sentinel-2 has a 5-day repeat cycle. So the time series of Sentinel-2 images is used as a superset here. Data is fetched from this set based upon the user requirements, that is the user region of interest and the time period of study that the user has declared or chosen. Finally, the analysis is performed over the Google Earth region. So the entire analysis is performed over the Google Earth region, as we will see in the demonstration. So the major or the basic steps that are involved are: firstly, we will take the Sentinel-2 data set. We'll take two inputs from the user. We'll take the region of interest and the start date and end date. Using this, we will filter the data. We will perform atmospheric correction over this data, and then we will calculate three parameters, that is turbidity, chlorophyll, and safety depth. And this is how it works. So firstly, as I've already said, that multi-temporal image filtering will be performed. This is based upon the region and the time. Also the cloud cover. So cloud cover is one property associated with all images from the Sentinel-2 dataset, which indicate that what percentage of this image is covered by clouds. So we apply an external filter that says that is more than a certain percentage of its pixels, let's say more than 20% pixels or more than 50% pixels in this image are covered by cloud, then we will drop this image. We will not take this image for further analysis. Otherwise, we will take it for further calculations. So that is also one kind of filter that can be applied to the image. Now, one region can be covered by multiple images. So we will combine all these images from the same date through the process of image mosaic. After that, we will preprocess the image, for which we will perform cloud masking. We will filter the images based upon the area covered by the image, and we will perform atmospheric correction. After the image is atmospherically corrected, we will separate the water and the non-water. Since our calculation or the mapping is only to be performed over water bodies, we need to separate the non-water region, after which we will perform the mapping of the animals. Finally, the data can be visualized and exported in the form of images, graphs, and animations. So this is what the user interface of the application looks like. On the left, we have the input panel, and this lets the user select the start date and end date. Also, the calculation to be performed. So the calculation to be performed can be turbidity, safety depth, or chlorophyll. We also have a clear map button, clicking on which all the results will be removed from the map. A type of AOI can be selected by the user. It is rectangle or point. So in this screenshot here, we can see that the rectangle type of region of interest is selected by the user. However, if the user only wants to check the parameters of a particular point, a particular location which the user is aware of, then we also have the select point type region of interest. And once the user clicks on submit button, these results are generated. On the right here, we can see this is an animation, below which we have a chart. On the top, we have different layers which can be added to or removed from the map. We have an export panel here, using which we can download these results which have been generated. And we have a map legend whose values can also be changed by the user. So this is an example of the Lonar Lake in Maharashtra, which changed its color overnight from a greener shade to a more pinkish hue. So we observe these images and we correspond with the satellite images along with the chlorophyll images. And what we could see, we can see here from the legend that the darker values, the values towards a brownish shade indicate high values of chlorophyll, whereas green and blue indicate low chlorophyll values. So we can see that as the color of the lake changes to a reddish color, the chlorophyll values also decrease. When the lake is greener in shade, the chlorophyll values are high. When the lake changes its color to a reddish or a pinkish shade, the chlorophyll values drop. And this can be seen, these values can be observed, and we can see that the chlorophyll values were dropping. So this happened in June 2020, and we can see here continuous decrease in the chlorophyll values. Another example is the region of Prayagraj in Uttar Pradesh, and this is the time in 2020 when the first lockdown was imposed in the country of India. And we can see these are the two rivers, Ganga and Yamuna. So we can see that when the lockdown was imposed, the turbidity of the two rivers reduced and the water quality increased. And this can be observed by comparing the satellite image from the turbidity image. You can see that on the 3rd of April, the turbidity values seem to be at their minimum because the colors of the two rivers were at their bluest shade, we say. And this can also be observed from this chart here, where you can see that on the 3rd of April here, the turbidity values were at their minimum. A similar scenario occurred in the Varanasi region of Uttar Pradesh, where we could observe the same variation in turbidity values during the lockdown that was imposed. Another application that has been created using the Google Earth engine is a flood mapping tool. So this determines the extent and the area of flood inundation. So we can see on the left we have a pre-flood image. On the right we have an image from the flood period. By comparing these two images, the water is segregated from both these images. Their difference is calculated to compute the extent and the area of flood. Now this brings me to the end of the presentation part. We move on to a brief demonstration of how you can get started with the Google Earth engine. Install anything to get started with the Google Earth engine. The Google Earth engine can be accessed directly through your web browser. So when you open your web browser and simply type Google Earth engine, click on Google Earth engine here, you will be redirected to this page. But here you can browse through the different categories available on the top right corner. First of which is the data sets. So let us go to the data sets and Just observe the different data sets that are available here. So when we scroll down, we see we have climate and weather data sets, such as surface temperature. We have satellite imagery. We have images from Landsat, Sentinel, MODIS series. Certain high resolution imagery is also available with the Google Earth Engine. Then geophysical data sets, such as the terrain data sets, LULC data sets are available. So a lot of data sets are available here, and you can also filter them by going to view all data sets. And you can, in this filter tab, you can type whatever it is that you want to search. So suppose I want some data sets related to forest cover. So I just type forest here. And when I type forest, all the data sets that are somehow related to forest cover will be listed down. I can choose to select any of these data sets, import it into my code in the Earth Engine, and start working with these data sets. Then you can also browse the data sets by tags. So we have different tags associated with each data. We have climate data sets, coastal data sets. So there's a lot of ways to filter down the data set that you require. Other than that, we also have data sets from the Landsat collection. We have Landsat 8, 7, 5, and 4. We also have data from the Sentinel and the MODIS series. Now we go to platform. Okay, before that, we would need to sign up for the Earth Engine. So when you click on sign up, it will simply ask your Gmail account. When you type your Gmail ID here and click on the next button, it might ask you a series of questions such as which institution are you associated with and for what purpose you want to use the Google Earth Engine. So when you answer these questions, you submit your form. Usually, you are granted access to a Google Earth Engine account, and it is free of cost. Of course, it is available for commercial use, but to begin with, you can create an account from your very own Gmail ID. Now you need to go to platform and click on code editor. So when you click on code editor, I'm not signed in here right now. I will open a browser window where I'm already signed in. So this is what appears. This is the code editor that I had already described in the presentation. So on the left, we can see these are all the scripts that have been created by me. These are all listed here. We have the assets tab where all the assets that have been imported to the Google Earth Engine are listed down. Now let us begin writing a very basic code, or let us understand how JavaScript works over the Earth without performing any actual geospatial analysis. Let us first understand how JavaScript works on the Earth. So any program or any language when we learn, we begin with a simple print statement. So here we will write print, and within the brackets or within the parentheses and the double quotes, we'll write whatever it is that we want. So the print statement is used for printing your results or anything that you want to print on the console. Now when I click on run, this is the console tab, and you can see welcome to JavaScript for GUI is printed here. Now these are variables in Google Earth. Any variable here is declared with the keyword var. So I declared a variable named message. To this message, I am assigning the value hello world. Now we print this message. Now if I click on run, hello world will be printed. Now variables can be of type string, that means variables can contain characters. Variables can also contain numbers. So here we have one variable called number which contains the number 5.6. And what I'm doing here is number is equal to number plus 10. So I'm just adding the value of 10 to the number. And now if I print this number, it will give me the value 15.6. So these are very basic or the initial steps that will enable you to get started with the project. Now other than strings or numbers, you can also have a list of numbers. So here I have a variable which is named list of numbers and it contains some 6 numbers within it. Now if I want to print an individual number from this list, I will use it with the help of the index. So indexing begins with 0. So if I want to access the first element of the list, I will say list 0. If I want to access the second element, I will say list square brackets 1. For the third element, I will say list square brackets 2 and so on. Now if I only print this list of numbers, you see the entire list is printed. Numbers 0 to 0, 1, 1, 2, 3, 5. Now if I want to print a particular number from this list, suppose I want to print the fourth element, then within the square brackets I will write the number 3. Now if I run this, only 2 is printed. 2 is the fourth element of the list. Other than this, we also have dictionaries. Dictionaries are used to store data in the form of key-value pair. So in this dictionary, we have one key called A, whose value is 1. We have another key called B, whose value is second value. So dictionary can be used to store a variety of objects. Within the same dictionary, you can store integers, you can store strings, you can also store lists within the dictionary. So if I say C colon, and if I type this variable, this is also completely valid. Now if I print the dictionary, it has 3 objects. The first has a key A and the value of 1. Second has a key B and value called second val. And third has the value C and the value is a list of values. This code editor will also tell you when you make any syntax errors in your code. So consider this statement, var test colon A. Now this is syntactically wrong because if you assign a value to a variable in JavaScript, you do it using the equal to operator and not the code. So therefore, this ID will indicate this red mark here, this red cross mark, indicating that this statement is not correct. So if I replace the colon with an equal to sign, the red cross mark disappears. You can comment your code by typing / before the line of the code. A commented code will not affect the code. So any commented values, any commented lines within a code are not considered, they are not compiled, it's considered as garbage value. It's just present, it does not have any significance. So the coder can use these comments for writing a description of what is actually happening in the code. Now let us say we have a function sum which takes in 2 parameters a and b, returns the sum of a and b. So this is a user-defined function. Now all the methods that we had seen earlier, we have only seen the print method here. This print is a JavaScript function, but this sum here that we ourselves have created is a user-defined function because the user is creating this function. So sum takes 2 parameters a and b and it returns me the sum of a and b. Now I will access this function using simply the name of the function and passing the parameters. It requires two parameters, A and B. So we say 5 and 10. Now if we print this addition of two numbers, it says 15 as expected. Now these are all, so far all the variables that we have seen are client side. Client side because before neither of these variables have we seen EE dot. So all the Earth Engine server side variables start with EE. So therefore these are all client side variables. Now the server side also has a number data type. So you can also create numbers using the server side data type, and this data type is called EE dot number. Let me just zoom into the code. I hope this is visible. So we can see EE dot number 8. So we have declared one number with the value 8. We have declared one number with the value 5. Now both of these numbers are server side numbers. Now if we add them, we cannot use the plus symbol for adding. We will have to use the server side method for adding. So the server side method that we will use to add two numbers is called add. Now this can be seen if you move to the docs tab on the left side. If you move to the docs tab and search and type number, you will get the data type EE dot number, and you will get all the associated functions with this data. So we have one function called add. If you click on it, you will see that this takes one left parameter and one right parameter. So using this, I'm adding two numbers, num1 dot add num2. Now the difference between these two additions is that one is adding client-side objects, one is adding server-side. So client-side operations are performed on your web browser itself. So this will be very fast. Whereas the server-side operations, firstly go to the Google servers, the result is computed there, then the result is sent back to you. So all that process will of course take some amount of time. So for very basic operations, very simple operations which you don't need the Google Earth Engine servers, then you don't need to use server-side objects for those computations. The computations which can be sufficiently calculated in your web browser itself, you can calculate it using client-side variables only. Because now we will see the difference. Now when I run this code, just observe how much time it takes for the first addition to be performed and how much time it will take for the second addition to be performed. Now if I click on run, please observe the console tab. Now the first result has already been generated, whereas the second number was still being computed. And this will obviously happen because the two numbers first will go to the servers, they will be added there, and then they will come back to the user. So of course it will take some amount of time. Now this is most of all the basic JavaScript that you will be requiring in working with Google Earth Engine. Other than JavaScript, you need to have awareness of the Google Earth Engine libraries. But what all functions are available in Google Earth Engine and how you can use them. So we quickly see how visualization can be performed using the Google Earth Engine. So for that, firstly, we have to import a data set. Now to import a data set, we can see the search bar on the top. So when I click on this, and if I start typing something, suppose I am typing here Landsat 8. So I will get the list of Landsat 8 collection. I can click on any collection that I want. Now I want surface reflectors data here, so I will type SR as well. So I get a more filtered list which says Landsat 8 surface reflectors. I click on this data set. I will be redirected to this, or rather this pop-up window will open, which will show me the description of this data set, what this data set contains. It will show me the different bands that are available. So each image of the Landsat 8, the first band is ultra blue, the second band is blue, third band is green, and the corresponding wavelengths are also displayed here. We also have different image properties that are associated with each Landsat 8 image. We have the cloud cover property. We have Landsat ID, which is a unique ID for every Landsat image. On the left, you can also see the availability of the dataset. The Landsat 8 imagery is available from April 2013 till the present date. To import this dataset, you can either copy this particular line, and you can paste it into your code, or you can simply click on this import button here. When you click on this import button, this dataset will be added to your So then we also import a geometry. Import a geometry or create a geometry. Create a geometry why? Because we want to restrict our connection with respect to some space. Now in order to draw the geometry on land, there are two ways to compute geometry. The first way is to specify the coordinates from within the script. For this, we will be using the data type ee.geometry.rectangle, and we will specify the 4 coordinates of the rectangle here. Another method is to draw the geometry on the line. For this, we will choose the rectangle or the polygon, and we will simply draw this geometry on it. When we finish drawing this, we will see that the geometry variable has been added to our map. So these are the 2 ways in which we will create geometries. Now once the geometry has been created, let us call this as GEO, the name of the variable is Geo. Now we will add this Geo variable to the map. Now for adding any variable to the map, we will use the function map.addLayer. So it adds a layer to the map. Now let us see when we run this. You can see in the layer manager, layer 1 is written. So one layer is being added. And that is zoom out of the map to see where this layer exists. You can see a black boundary here, and this is the geometry layer which we have added to the slide. If you want to use certain colors to add this layer to the map, you can specify these parameters. So here I'm specifying color is red. Also specifying a name for the layer. So name for the layer is geometry. By default, the name of the layer will be layer 1, layer 2, 3, and so on. But we can also specify our own name to the layer. False means that the layer will not be added by default. We will have to tick it from this checkbox in order to display it. 0.6 is the opacity of the layer. We will see this when we add the layer to the map. Now if I click on run, so by default this layer is not added to the map. So if I click on this checkbox, a layer will be added. This layer is now red in color, and the name of the layer is also geometry. Now this is the opacity. This bar that you can see, if we move it towards the left, we see that the layer goes completely transparent. And if we move this towards the right, we see that the layer becomes more or less translucent. So this is the opacity parameter, which can also be changed while adding this layer to the map. Now we can also center the map around an object by using the method map.centerObject. So let us say my map is currently at some random location in the world. Now if I click on run, since I have the map.centerObject, to this I am passing the parameter GU, which means that I have to center my map around this object. Now if I click on run, my map will be automatically moved to my region of interest. Now this 10 value here indicates the zoom level. This zoom level value ranges from 1 to 24, 1 being the highest zoom level and 24 being the lowest. Now we will filter our data set on the basis of date. So our data set, initial data set is called image collection, as you can see from the import section. So we will do an image collection dot filter date. Filter date function is used to filter the data set based upon some date. To this, we specify two dates. First is 1st January 2020 till 1st of April 2020. Now the second date is not inclusive. That means if we specify 1st of April 2020, this will fetch images till 31st March of 2020. So you always have to specify one date more than the actual date that we desired for the filtering operation. Now let us print this data and see the result. You can see in the console the image collection is being completed. And as expected, it says that the collection query aborted after accumulating more than 5,000 elements. And why did this happen? Because if we are trying to print this data and we only filter it with respect to date, it still contains all Landsat images from these 3 months across the globe. And these account for a lot many months, which the Google Earth engine does not permit you to print. So you further need to print it with respect to the region. So here I am doing the simple data.filter bounds. Now in order to filter the collection by a region, I use the function filter bounds and will specify the geometry within the brackets. So now let us see whether we are able to print this data set. Now since we have taken a very small region of interest, this data set for these 3 months contains only 6 elements. If we expand this image collection, you will see under features, we can see 6 images are present. Each of these is an image composing of all the Landsat 8 bands and several properties with each image. For example, we have the cloud cover, we have the Landsat ID. So we have a list of 6 images. Now let us filter them on the basis of cloud cover. Now we will take only the images which have a cloud cover less than 10. So if we expand the first image here, we see in the properties tab, this has a cloud cover of 22.37. If we take a look at the second image, this has a cloud cover of 45%. So we only need images which have cloud cover less than 10%. Now let us print this and see how many images we get. Now we get only 3 elements. So we had 6 elements when we filtered our data based upon the time and the region. When we further filter it on the basis of cloud cover, we have only 3 images remaining. Now let us add this image to the map. Now in order to add this, I'm using the data.mean. This data is a collection which has 3 images. I can either display an individual image from this collection. I can also use a function such as mean, which will take a mean of all these 3 images and display it on the map. Then I have this params. This variable is visualization parameters, which indicates which all bands I will be using. So I will be using bands 4, 3, and 2, which is band red, blue, and green for the Landsat 8 collection. I will also specify a min and max value, which is basically equivalent of histogram stretching operation. So bands, how did we determine which band of Landsat is red, which is blue, and which is green? For that, we will go to the top of our code. We will go to our collection. We will go to bands, and here we can clearly see the name of the bands. So band B4 is the red band. The green band is called B3 and the blue band is called B2. So if I add this layer to the map, and we are calling this image as mean image NCC. this natural color composite. So this image is added to the map. Now this is the entire Landsat 8 image. We can see the presence of some clouds in this image as well. Since the cloud cover was less than 10%, but there was still some cloud cover remaining in this image. Now, in order to add a false color composite to the map, we will just need to change the bands. For the FCC, I am using bands 5, 4, and 3, which is the NIR band, the red band, and the green band. So this is the FCC image that has been added to the map. So we have it. So if I uncheck this, we need this, I can see the natural color composite. And on top of that, we have added the layer of the false color composite. Now, we only selected a very small region for our geometry, but here the entire Landsat 8 image is being displayed. Now, we don't want to work on the entire image, so we can also choose to clip this image based upon our geometry. So for that, I'm creating a variable called mean, and I am taking the mean of the data. Then I create a variable called clip, and I'm clipping this mean image with respect to my region of interest. Now, if I add this clipped image to the map, this is the clipped. So we can see the entire Landsat 8 image in the background, but a very small portion of the clipped image in the foreground, which is clipped on the basis of the region of interest. Finally, we will see how this image can be exported to the user's system. So for that, we will use the function export.image.google Drive. If you go to the docs tab and you type export, you can see the different functions or methods that are available. I will click on this method, export.image.to-drive. It indicates the different parameters that are required. So firstly, we need to specify an image that we actually want to export. A description for the image. It can be a name for the image. This is an optional field. You can also specify a folder, which will be the Google Drive folder to which you want to store this data in. So you can give the name, prefix of the name, you can specify the dimensions of the image, you can specify the region and the scale, all of that can be specified. Here I'm using the image, I'm exporting the clipped image, a description is being given, the folder is being specified, the region is of course geo, scale is scale of 30. Since this is the scale of Landsat 8 images, I've taken a scale of 30. Now when I click on run, I will see that the task tab gets highlighted to yellow color. When we move to the task tab, we will see this has been added, which is LS8 mean image. Now if I click on run and simply click on run again, this image will be added to my Google Drive in the folder name GEE demo. This will take a couple of minutes to run, probably 2 to 3 minutes. After which you can go to your Google Drive, search for this image and download it to your desktop or your own system. Now if you take a look at the inspector tab, so I've moved, I clicked on the inspector tab. Now we see that the cursor has changed. Instead of the pan, we now have this cross bar. Now if I click on any point on the map, here we can see that we have the individual values for all the layers for this particular pixel. So we have one image called mean image NCC, which was added to the map. So we get the value of all the layers for this particular point. We get the same for the next layer, which was added, which is mean image FCC. And we also have mean image FCC clipped, which is another layer added to the map. But at this particular pixel, it says that there are no unmasked pixels available. Probably because this is out of the range. Yes, that was clearly out of the range of the clipped image. Now, if I click on any point within the clipped image, it will give me the value of all the bands for all the three layers. So this is the purpose of the inspector tab. Other than that, there is a lot of documentation available for the Earth engine, which I would suggest you to definitely go through. In order to get started with the Earth engine, you would need to first go through the documentation and try a lot of examples. On the left hand side, you can see already certain examples are provided by the Google Earth engine for your reference. So you can start by taking a look at these examples. And you can also go to the Google Earth engine documentation. We have platform and then documentation. So if you go to this, you will see there are guides available. So you can click on any. If I go to image and I click on image overview, it gives me how to get an image from an image collection and what are constant images. So it is explained in good detail how all these data types of the Google Earth engine should be used. So other than that, there is also you can also ask questions or raise bugs. There's also a community available, the Google Thinking Forum. So if you get stuck anywhere, there are people there to help you out. Now that is all that we'll be covering today. I'll take a look at the questions. So the accuracy of the height generated from Google, now there are already certain terrain data sets available on the Google Earth engine. Other than that, you can also use some data sets to generate your own elevation data sets. The height or the elevation resolution of the data sets that are already available will be mentioned along with those data sets. It will be mentioned depending upon the data set. And if you use certain other data sets to compute the height or elevation by your own, then that will also vary upon the data set and the calculation that you perform to generate the height. Then again, installation is not required. You just need to sign up for it, and you can get started with it. It's very simple to start with the Earth engine. So the accuracy of the operations, we can say the scale of the operations can be specified by the user also. So different operations on the Earth engine, the different calculations that you perform, along with the calculation, you can also specify that at what scale you want to perform this calculation. Now here I have an answer 8 image, and if I want to perform this any calculation on this image at a scale of 30 meters, that is possible. I can also choose to perform calculations over this image at a scale of 100 meters. So another question is, are the images on Google Map or Google Earth live or they are rectified? So if an image is acquired today, it will be added to the Earth engine in a span of 2 days. And yes, these images are rectified. They are corrected, geometrically, radiometrically corrected. They are saved on the Google data centers, and you just have to import them to your data by writing a single line of code. You don't need to download it to your desktop. You can just use it on the Earth engine itself. So, fusion of multiple images. Now, if you want to combine multiple images, firstly, it depends whether they are from the same data set or multiple data sets. So, in order to combine images from the same data sets, you can use simple operations available with the Google Earth engine. For example, I'm going to the Docs tab right now, and if I type mosaic, we get two functions. One is image mosaic and one is quality mosaic. So if I click on mosaic, it composites all the images in a collection. So if we have multiple images, it will combine them into a single image. We can also use functions such as the median, which is applied over an image collection, which reduces an image collection by calculating the median value of all the pixels. Another function that is available is simple composite, and this is specifically for the Landsat series. So you can see ee.algorithms.landsat.simple composite. If I click on this, so this computes the Landsat composite from a collection of Landsat series. So there are several methods available on the Google Earth engine for such an operation. Okay, another question is that I'm talking about map function. No, this is not the same function as the maximum likelihood estimator. We of course do have a maximum likelihood operation or function available with the Google Earth engine, but this map is not the same as that. This map is simply like a for loop, which helps you perform the same operation over and over again over all the images that are available. Over suppose we have a collection of here we saw we have a collection of 6 images. Is it printing these images? So here we have 6 images. Now if I want to perform some computations, such as I want to remove all the clouds in these images. Now doing this one by one for each image would be problematic. So I am using this map function to simply perform the same operation over all the images that I have. So that is the only purpose of the map function. However, it is optimized for use over the Google Earth engine and it is highly efficient. So how can we see image of previous years in Google Earth engine? That's another question. So here, this is what I have done. Taken the image collection, use the operation filter date, and you can specify whichever date that you want to specify. This can be any date in the past, provided that the dataset is available for that. Now, this is Landsat 8. So I cannot specify a date lesser than 2013 because Landsat 8 was not launched before that. So I can specify any date from 2013 to 2021 and it will filter out those images for me. If I specify a date before 2013, then I will get a blank data set as the output because no images are available because Landsat 8 started its operation in 2013. So I think that covers all the questions. So the last question by Swati, if I need to understand this properly, I think you mean to say that how can we perform different work on the Earth engine, different kind of work. So that depends on the very same data set can also be used to perform different kinds of operation. Now we have a Landsat image here. We can study the water bodies. We can study the forest area. We can study land use, land cover changes. So the very same data set can be used to perform a variety of functions. Firstly, other than that, there are also several data sets available. So if you want to perform any atmosphere related uh, work, if you want to do, there are several atmospheric data sets available. So you can import those related data sets into your code. And the technique is the same. So depending upon your analysis, you will write the code differently. Right? I think that brings me to the end of the question answer session also. Thank you all.